Good morning, everyone. I'm Pankaj Niroula from ETC Lab with William and Mary, and this is going to work with my lab mates, Aashutosh, Collin, and my advisor, Stephen Herwig. This is about bringing DNS caching back after Oblivious DNS had to let go of it for privacy reasons. So encrypted DNS, whether it's DNS over HTTPS or DNS over TLS, encrypts the data in transit. But just encrypting in transit does not really solve the problem that the resolver has to decrypt all of it. And so the resolver is able to see like who's asking, and a few number of resolvers actually see all of the large share of the traffic. So it's one vantage point which holds all of your entire browsing history itself. Now, CODoH solves this problem by splitting the request into two hops. Um, so the client actually encrypts end-to-end, the request end-to-end to the target. The proxy only sees the address of the client, but it does not see the query itself. The target, on the other hand, sees the plaintext query, but does not see who is requesting it. And so um, with this, like neither of the parties, neither the proxy nor the target sees both, and this is because they can't collude. This is deployed at scale today. Apple's iCloud private relay actually uses it, where Apple runs a proxy and Cloudflare runs the target. So why is caching hard? Caching is hard here because CODoH brings on brings unlinkability by actually encrypting using fresh randomness on its request. And that makes it such that the cache can't really cache it. Now, this would also keep away the biggest performance lever that a shared DNS infrastructure would have, which is the performance benefit. Um, so every query has to be the full two-hop path, which is like 48 milliseconds at median versus 18 milliseconds from a cache. So why don't we just add a shared cache? Because a shared cache is a shared state and a shared state is a state channel. Um, so imagine a classic attacker where the adversary times a request, and um, when it runs a request, like if the response is fast, it can know that someone had already requested the query, and if it's slow, then it can know that it's not already in the cache. So, um, so the proxy. So who do we think here is we keep as the adversary? We keep the strongest adversary here, which is the proxy operator itself. The proxy is the cache, and what this also brings up is the proxy can now probe as a client. It can queue the traffic and isolate a victim's query. It can drop, replay, or withhold inserts into the cache. It can also restart the cache, and it can also watch the timing and memory access patterns. So the non-collision aspect of CODoH is still kept, and then everything else the adversary can do. Now, since we are adding caching, there's a performance benefit, but we also need to guarantee a few extra things. The first thing is that the process would never really um, respond to the client with a response that's not authorized by the target, and that is still. So this has to be always signed and verified so that there's no possibility of poisoning, tampering, or still replace. Second, to a proxy, all the hits must look like a mesh itself. So regardless of whatever is being queried, there should be the same sort of string states, same packet sizing, and the timings should be equalized as well. This would make it such that probing, scheduling, as well as restarts would reveal almost nothing to the proxy. And third, the proxy should be able to tell if two requests have a sync. So this is if it is possible, then that would make it so that the clients can get profiles. So that's not possible as well. So let's design a obvious solution. We'll start with putting the cache in an enclave in the proxy. Um, Now, if you just put it in an enclave, what that happens is like it makes sure the confidentiality and integrity. But SEX, the enclave does not really ensure that it hides the access patterns. So what this means is the the entries that are in the cache that's visible, the change in entries is visible when they are computed is visible, as well as like which memory or lookup actually touches is also visible. So we'll talk about each of the leakages and the differences. So first of all, let's look at the leakage of a bit skip. Imagine the proxy takes a snapshot of the cache script, meaning it queries and enumerates everything that's in the cache right now. It blocks the traffic and then just allows one client query to pass through. Now it takes the snapshots again. The difference now in the cache script would point to just the query that was being asked by the client itself. Um, so this is known as the set difference attack. And for this, like, we don't even need to decrypt anything at all. So the solution to this is adding global responses, where for every client request, the proxy for every client request, the target is going to respond with the real versus real plus key copy responses. The copy responses are basically just responses for domains to look like similar traffic, where they are going to add into the anonymity set. So now when the proxy can snapshot again, it's going to see that there's the differences in k plus 1 number of inches. So the probability is now 1 by k is the Pascal's k plus 1. The second case is in timing. So every time there's a request, every time there's a request, there's like, say for example, k plus 1 copy inserts. That instantaneous event is also going to allow the proxy to know that certain query is getting all the different responses. So this should not be visible. We solve this by doing patch commits. So basically, um, um, like we keep a lot of commits pending in a pending tree, and then only patch it at a certain large enough anonymity set. So one commit mixes many queries at this point. So the probability of identifying a victim's domain becomes at most 1 by 1 plus pk. This p.k is the privacy performance knob. We'll talk about it again in evaluation. And then the SDF also does not hide the access patterns. So if the proxy is pointing a domain and then it notices the slot that lights up in the page, and if there's a query again and it lifts up the same page, then the proxy can identify what query has been queried. So we solve this by using ORAM with PathORAM. The difference with PathORAM, um, every axis is going to pull in make sure there's like a random uh, operations, like a similar set of random operations, so that you can really identify from that. Um, so the design overall looks like this. There were the leakages, which are all of them were solved by the differences we talked earlier. When a client has to actually request a query, it sends a query to the enclave as well as the target. And if there's a cancel, then the enclave responds first. And when there's a cache miss, um, when there's a cache miss, it just resolves back to baseline order itself. So there's two requests going ahead and then two responses coming back, but it's all same in the wire. CODoH is deployed as an extension to the CODoH stack itself, so we really deployed this using DNS and off-the-shelf stack. There are So we did this as a DNS plugin. For Enclave, we run this as an Ego SES Enclave. Regardless of hits or miss, it's everything same in the wire itself. In the ANKit, there's a narrow trust boundary as well, very few operations being run over there. And then to run apples to apples comparison, we ran all of these different configs and identical infrastructure across 3 different Azure regions. So what does that all that buy? We find that CODoH is 2.7 times faster than Odo in warm workloads, and in a zip realistic workload, we find that it's 2.2 times faster, and on cold where it's all misses, it's just 0.9 times slower. Again, like because it falls back to Odo baseline, so it does not really matter. There's this was more of this in the paper as well. Like I'd be happy to discuss in the poster. Um, the takeaway is with CODoH, we restore proxy side caching without giving up the segregation of knowledge. The performance is regained without losing the privacy. Thank you. I'll be happy to answer any questions in the poster section.